Okay, welcome back, you guys. Here's our lecture for today. Last time we finished up talking about G, the Gibbs energy, and the Helmholtz energy, and now I want to get into a little bit about why the Gibbs and the Helmholtz energies are so useful. Should have finished this last time, but we just need to tie up one loose end before we move on. Okay, so just like with delta H that we found before, we can define the delta G for reactions. Okay, so we can define the delta G for the reactions, and it turns out that delta G is more useful than delta A, simply because delta A is a function of S or T and V, whereas delta G is a function of or has natural variables of T and P, excuse me. So in this case, when T and P are constant, delta G is much more useful. We can define a delta G formation, or delta GF, and this is the Gibbs energy of formation. And it's exactly the same or similar to delta HF, which is the enthalpy of formation. We can also define delta GF0, and this is the Gibbs energy of formation in standard form. Okay, so if you have a standard delta G formation, that means that you have a standardized reaction for that formation process. Okay, and from this we can build delta G reaction, which is using Hess's law, the sum over the products of all the delta G standard formations for the products minus the reactant delta G standard formations. Okay, so for the overall reaction, we can figure these out. And typically, you'll find these types of values here and here listed in a table, just like you would delta H formation or S formation. Okay, so that's delta G reaction, and just like you would use delta H, you can use delta G to find the delta G for a specific reaction. Okay, let's go back to the same, or these four independent energy quantities that we've now determined. Okay, so we have four independent energy quantities, okay, that we've determined. These are, starting with the internal energy, du is equal to T ds minus P dV. Okay, so then the natural variables for these, in this case it's u as a function of S and V. Okay, dH is T ds plus V dP. In this case, H is a function of the natural variables S and P. dA, these are the two new ones, is given as negative S dt minus P dV with natural variables T and V. And finally, dG is equal to negative S dt plus V dP with natural variables T and P. Okay, so that's how you can stick those together. This is kind of a summary of all of these four independent energy quantities that are defined using P, V, T, and S. Okay, and here on this side I'm giving the natural variables for each of those. Okay, so what can we actually do with this information? It's a summary here, but what can we actually do with these definitions? Okay. Whoa. Okay, what can we actually do with this information? To determine this, let's start out by looking directly at U. Okay, so let's look at U in particular. U is a function of the natural variables S and V, so entropy and volume. Okay, and if we recall from chapter 3 here, okay, so we're going to do some recollection from chapter 3. The overall change in U can be separated into two components. Okay, one, how U varies with respect to S, and two, how U varies with respect to V. Okay, and we can write these out using partial differential equations. Remember partials, guys? Okay, we can use partial derivatives to actually write out how U varies with both with respect to both S and V. Okay, so number one, how does U vary with respect to S? We can write this as partial of U with respect to S, keeping V constant. Okay, and number two, we can write how U varies with respect to V, keeping S constant. And from these, whoa, my brackets are weak today, guys. From these two, we can form the overall du by putting them both together. So if you recall from chapter 3, du is therefore given by the first one, the partial of U with respect to S, with V constant times ds, plus the partial of U with respect to V with S constant times dV. Okay, so this is the overall change in U. But if you remember from the natural variable equations we have up here, okay, so these guys here, we can also write the overall change in U as equal to T ds minus P dV. I'll leave that there for just a second to get you guys to see why this is so useful. Right? If you see that now, you see how those are equal. So now we can actually make an equality between those two pieces that are circled. Okay, so we can say that the change in U with respect to S at constant V is actually equal to T. And we can also say that the change in U with respect to V at constant S is equal to negative P. Okay, so this is giving us the change in U. Whoa, that's bad U. The change in U with respect to S at constant V is equal to T. So if we just measure the temperature, we know the change in U with respect to S at constant V. It's very easy to measure the temperature. It's not so easy to measure the change in U with respect to S at constant volume. Okay, so now you can see the power of these thermodynamic principles. Now we're saying, in this case, that the change in U with respect to volume at constant entropy is equal to negative pressure. Now you can imagine how difficult it would be to design an experiment where you had constant entropy. Very difficult. But it's extremely easy to measure the negative of the pressure. And what we're saying here through these relationships is that they are equal to each other. So if we just measure the pressure, we know the change in U with respect to volume at constant entropy. And that's why this is so powerful. Okay. First of all, we can measure T and P directly. Also, these relationships here. So I only did du, right? I can do all of them. I can substitute in and look at each and every one of the above state functions, and we can then substitute complicated partials with simple state variables. Okay, we can substitute these complicated partials that we find in other derivations. We can just simply plug in the temperature or the pressure or the negative pressure, and it's equivalent. Okay, so this helps us with derivations as well. And we can write these out for all four of the state functions. Okay, so let's do that here. So for du, I'm going to rewrite them just to keep it all consistent. We have d, or the partial of u with respect to entropy at constant volume is equal to t. The partial of, or the partial of u with respect to v at constant entropy is equal to negative p. Okay, and du has the natural variables s and v. Okay, then we can go to dh. I can do a similar derivation as I did above, and I can derive dh, or the partial of h with respect to p at constant entropy is equal to the temperature. And I can derive the partial of entropy with respect to pressure. Oh wait, I already have that one. Sorry, this is backwards. Okay, the partial of entropy with respect to enthalpy with respect to entropy at constant pressure is equal to temperature, and the partial of enthalpy with respect to pressure at constant entropy is equal to the volume, with natural variables in this case of s and p. Okay, and then we can do dA. So the partial of A with respect to temperature at constant volume is equal to negative entropy. The partial of A with respect to volume at constant temperature is equal to negative of the pressure. Okay, with natural variables in this case of temperature and volume. And then finally, delta G. We can define delta, or the change, the partial in G with respect to the change in temperature at constant pressure is equal to negative S. And the change in G with respect to the change in pressure at constant temperature is equal to the volume. Okay, and again, let's write out the natural variables here for G, which are T and P. So now you guys can start to see the power of thermodynamics, or the power of these four independent energy quantities being defined in terms of their natural variables. We can actually begin to replace possibly difficult things to measure. Okay, so something that's difficult to measure, or we can replace something that's maybe complicating up a derivation. We can replace that directly with a very simple state variable. Okay, so this makes a lot of things more simple, and I think makes a lot of things more powerful as well, as we will see moving forward. Okay, so let's first discuss this. Why in the world, or I guess it's kind of obvious why it's so useful, but let's explicitly state that. Okay, so why so useful? Why is this so useful? Let's do an example. if we know G, if we know that G is a function of T and P, okay, we know this, and we know that, or we know how G varies with T and P. Okay, this means that we also know S and V. Okay, we also know S and V. Because of this, or therefore, we can determine the other state functions. Okay, we can determine all of the other state functions by simply knowing that G is a function of T and P, and if we know how G varies with T and P, we can determine all of the other state functions. Okay, let's show this in an example. Since H is equal to U plus PV, okay, and G is equal to H minus TS. If we take this H and plug it in here, we get G is equal to U plus PV minus TS. Okay, now let's solve for U. U then, therefore, is equal to G minus PV minus TS. I can substitute in the partials with respect to G for both of these two values. Okay, so this is just the partial of G with respect to P of T, and this is just the partial of G with respect to T with P constant. So I can plug those guys back in. Now I can define U in terms of G only. So it's pressure times the change in G with respect to P, T constant, minus T times, wait a minute, I'm mixing this up. Oh no, I'm not, I'm good. Minus T times the change in G with respect to the change in T at constant pressure. Okay, so this is an expression for U with respect to G. And we can do this for all the other state functions. Okay, so you can determine all state functions if you know about one. Okay, and this is extremely powerful. If you know the values for the proper changes in one state function, i.e. the changes in the natural variables for that state function, you can use the equations of thermodynamics that we've laid out above to determine all the other state functions. Okay, you guys should be gasping in alarm at this point. This is very, very powerful, and it begins, it helps us go from the first stages of thermodynamics, which is just defining these things, into the next phase, which is actually using these things in a practical way to help us inform ourselves about the physical world. Okay, so this is the first step. The thing is, though, we can take this one step further. Okay, this isn't far enough. We can go further. Okay, let's go one step further. Okay, so first of all, we need to consider the state functions in terms of their natural variable equations. And what I mean when I say that, so we have a state function in terms of natural variables. What I mean by that is, for example, dH, the overall change in the enthalpy, is equal to the change in enthalpy with respect to the entropy at constant P times ds plus the change in enthalpy with respect to pressure at constant entropy times dP. Okay, so you can form this from any of the state functions in terms of their natural variables by knowing the natural variables for the state function itself. Okay, so you can form this for h, you can form it for u, you can form it for g, etc. Okay, let's just use h for now. Okay, all of these in general are going to have the same general form. Okay, they all have two terms. Okay, one is the change of the state variable with respect to the change of the state function with respect to one state variable. And the other is the change with respect to the second state variable. Okay, in the case of dH, it's the change with respect to entropy, and the second is the change with respect to pressure. Okay. One thing to note here is that for these two changes, since this is a state function, it doesn't matter which change happens first. Okay, it doesn't matter which change happens first because it's a state function. It just depends on the initial and the final values of that state function. Okay. The second thing that we can notice from this is that since it's a state function, as long as both happen, at some point, doesn't matter when, at some point, the overall change in that state function, for example, dH in this case, has the same value. Regardless of when they happen or how they happen, as long as they both happen, dH is always going to have the same value. Okay, this is the first principle of being a state function. Okay, so we're going to take these two ideas and we're going to mathematically describe a state function using a generalized formula. Okay, so let's take these two ideas and generalize it. Okay, we're going to generalize it into some state function. We're going to call this state function f of x, y. Okay, this is our generalized state function. If we look at the overall change in f, we can define this as df dx with y constant times dx plus the change in f with respect to the change in y with x constant times dx. Okay, so these are the two terms. Okay, now the next question I want to ask about this is, can we determine the simultaneous change in f with respect to both x and y? So simultaneous both x and y. Can we determine that? Basically, all I'm asking here is a second derivative. Okay, use a second derivative. So we can derive something, or take first derivative and then take a second derivative with respect to the second variable, and therefore you have the simultaneous change in f with respect to both x and y variables. Okay. Since this is a state function, okay, since it is a state function, it doesn't matter which order we go in. Okay, it doesn't matter which order. So order doesn't matter. And thus we can define the change in this function with respect to the change in x of the change in f with respect to the change in y with x constant and then with y constant is equal to the change in the function with respect to y times the change in f with respect to x with y constant and then with x constant. Okay, let's break this down a little bit. This inside part is taking the derivative of f with respect to y. And then it's replacing that inside this brackets, and it's taking the derivative of that result with respect to x with y constant. Okay, this side is taking the derivative with respect to x, and y is constant, and then it's taking that result and taking the derivative with respect to y and x constant. Okay, and what this is saying is that these two are equal simply because of the way that we set it up, and you can actually verify that for yourself. Okay, so these two values are equal. This very interesting thing that we've just determined, that it doesn't matter the order in which you take the two derivatives, they're going to be equal to each other, is the first criteria for df being what's called an exact differential. What's going on? For some reason my pen is not writing anymore. Oh man, we've got a freeze. Okay, I'll start again. I'm going to stop here, figure it out, and then I'll come back to you.